In this video, we're going to talk about what happens in the brain. What changes in the brain during that learning response? What allows that memory to be stored in the brain? So we're going to start off talking about what is the Hebbian synapse, and then a little bit of an understanding about what LTP, or long-term potentiation, is. Perhaps you remember hearing the phrase, cells that fire together wire together, at some point throughout the semester. Well, that's the Hebbian synapse. So if you look here, you have this postsynaptic neuron, and you have all this input from these presynaptic neurons. Now, these ones labeled here in yellow, they fire at the same time. So instead of just one cell firing and causing a weak depolarization, you have synchronous activity in all three, causing a great amount of depolarization. So think back to those chapters when we talked about EPSPs and IPSPs and how working together, cells are more likely to fire or cause an action potential in the postsynaptic neuron than just one by itself. Now, these ones down here, they don't fire together. They don't fire together, and on their own, they don't fire rapidly enough to cause enough depolarization in the postsynaptic neuron to cause an action potential. So what results? These ones firing together, causing an action potential, means that these cells, these presynaptic cells and this postsynaptic cell, they're firing together. And so thus they wire together. So as a result, you see this change in the plasticity. You see changes presynaptically that can be measured postsynaptically. Here, these ones didn't fire enough to cause action potential, so there's lots of ineffective inputs, and so these connections disappear. And again, thinking back to some of those things we learned early in the semester about cooperativity, associativity, and specificity. Now, this type of wiring and changes in wiring might be very critical for what we've talked about as associative learning. And remember that associative learning was classical and operant conditioning, the types that we discussed. So here, just to give you an idea, here's our air puff, and it has a very strong connection. Here's kind of this black box, and somehow it causes that eye blink response. Well, if you pair this air puff with the tone, and the tone had a very weak stimulus, not enough able to cause that eye blink response, but you pair this input, sending action potentials, with this input, these cells are firing together, so they're going to wire together. Now the tone on its own can create that eye blink response. So that brings us to long-term potentiation, and what actually is it? And there's another video that you'll watch to help you further understand it. But basically, again, the postsynaptic cell, that dendrite, is bombarded with stimulation. One or more axons bombard a dendrite with stimulation. So here, under our normal conditions, you have one action potential releasing that neurotransmitter into the synaptic cleft. You're going to have sodium enter through an AMPA receptor, and if you have enough, you're going to have sodium and calcium enter through the NMDA receptor. Now, because these cells are firing together, it's going to increase the synaptic strength, and then the next time that happens, you're going to have, by the same action potential, you're going to have more neurotransmitter released, which is causing a bigger input here, and then the response here is also, in the postsynaptic cell, is also going to be greater. So the synapse becomes potentiated. It becomes more responsive, is another way of saying that. So the synapse becomes potentiated. Postsynaptically, it's more responsive. So this is what the depolarization would look like originally, and after these cells fire together and wire together, this is what that potentiated depolarization would look like. Here's just another diagram showing you different type of wiring. So here, again, showing you that here, strong stimulation from one axon is going to cause an action potential here. The synapse is going to be strengthened. Here you have a pairing of strong stimulation with weak stimulation. This synapse is also going to be strengthened because cells that fire together, they wire together. Here, no stimulation, axon is not going to be strengthened, probably going to be weakened. And this is what you would record in that postsynaptic cell when you get stimulation from this or this neuron after they've wired together. So the biochemical mechanisms of LTP involve changes at glutamate synapses. They're primarily in the postsynaptic neuron, although there are some presynaptic changes that are very important. And the main glutamate receptors involved are AMPA receptors and NMDA receptors. And that's just kind of showing you what this would look like here. Here's our presynaptic terminal. Here's our AMPA receptor. Glutamate's released. Glutamate binds that AMPA receptor. It allows sodium to enter. Under normal circumstances, the NMDA receptor is blocked by this magnesium. So even though glutamate's stimulating it, it can't allow anything to enter through its ion channel because of that magnesium block. In order for that magnesium block to be removed, you need to have repeated stimulation or stimulation from multiple axons so that more sodium goes through that AMPA receptor, depolarizing that postsynaptic cell further. That removes that magnesium block, and then calcium and sodium can enter through the NMDA receptor. And we're going to go through all of these steps in another video in a lot more detail.